Okay, so hopefully the recording works. That way I can actually upload something to YouTube later today. We shall see. Not used to using OBS. It's been a few years. I used it when we had COVID times. Anyway, today we are going to talk about, that's right, more rates of change. Okay, more rates of change, but today we're going to be talking specifically about linear functions and how they relate to our quadratic functions and vice versa. In our previous lesson, we looked at rates of change from multiple representations. We looked at graphs, equations, tables, words, all kinds of stuff. In this lesson, what we're going to be doing is we're going to be considering rates of change specifically in straight lines and in quadratics, and that's it. That's just what this lesson is about. Before we can even start, though, we have to learn some vocabulary. What is a secant line? A secant line, thank you. I'm glad that you volunteered. I was just going to say it. A secant line is essentially any line that goes through a curve more than once. So before, we were talking about finding the average rate of change between 2 points on a curve, right? Well, if we connect those 2 points with a straight line, that is a secant line. And the average rate of change between those 2 points on the curve is the slope of the secant line. So it's not even new, it's just using new words to talk about the same thing we've been talking about. So now, when we find the average rate of change of a curve, we can think of it as actually being the slope of the secant line that goes through the two x's in question. Cool with that idea? Yes. All right. This is still the slope formula, y2 minus y1 over x2 minus x1. Question for me? Nope. Okay. So that's all we're doing. We're finding average rate of change, doing it the same way we've been doing it, plugging in x's to get y's, rise over run, and I'm going to call it the slope of a secant line. Here we have some linear equation. It passes through 0, -3, and 4, 3. I'm just going to color in the 2 dots in question. We've been instructed to explain how we know that this is the equation. This equation is in slope-intercept form. Y equals mx plus b. We can see that our equation, our graph, that's what I want me to say. We can see that our graph has a y-intercept at -3. Since the y, okay, already, see? Since the y-intercept is -3, b equals -3. And as far as the slope is concerned, let's just calculate it. (3 minus -3 over 4 minus 0). That's 6 over 4, which, yes, does reduce to 3 over 2. Thank goodness this is the equation of that line. Otherwise, none of this would have made any sense. So all we've done so far is show that we know how to find the equation of a straight line. This question, I feel like, is too ambiguous right now. But it says, what do you notice about the average rate of change for a linear function? Okay, let me ask you a different question first. If I had chosen 2 different points than the 2 that I have here on this line, would I have found a different average rate of change? No. Why not? Because what? Because linear functions have a constant rate of change. And that's actually what you're supposed to notice about the average rate of change of a linear function. Constant rate of change. Yes, sir?
This might be a really stupid question. I'm sorry if it is. But, can you quickly explain the difference between rate of change and slope?
Constant rate of change. Not much difference between rate of change and slope. But we can't say slope at a single point on a curve. We can say instantaneous rate of change. But if you say slope, it implies that you're doing x2 minus x1. And if it's instantaneous, that's 1 x value, and you try to be dividing by 0. So it's just being picky about the terminology, to be honest with you. But in all reality, rate of change means slope. But when we're talking about a curve, we have to say average rate of change if it's over 2 points, or instantaneous rate of change if it's a single point. It's not a stupid question at all. London? Oh, okay. I answered the question. Fantastic. Yeah, it's not a stupid question at all. It's just being picky about the verbiage. That's all it is. When it says how is the average rate of change related to the equation itself, it doesn't, look, I drew all over my pinky. It doesn't mean, oh, it's the slope of the equation. No, we get that. No, what it means is what does it tell us about how the x's and y's change in relationship to each other? Because remember, the first lesson is called change in tandem. Change in tandem is a really big deal to AP pre-calc and actually calculus. Change in tandem is a big deal. So how is the average rate of change related to our function? What does it tell us about our function? It tells us for every increase of 1 for x, y increases by 1.5 or 3 over 2. It's literally just telling you this is what happens when x goes up. If x goes up 1, y goes up 1.5. Or you could say if x goes up 2, y goes up 3. Could have said that as well. It means exactly the same thing. They're both correct. So far we really haven't said anything much more than what we would have already learned in Algebra 1, right? Linear functions have a constant slope, and this is what slope tells us, literally rise over run. Something slightly different is he's used the grid at the right to sketch a graph of the function that represents the average rates of change of our linear function. Huh? Here's what it means. What's a good color? Orange feels good. Let's say instead of plotting x comma y's, let's plot x comma rate of change. At x equals 1 on our straight line, what is the rate of change? 3 over 2, which is 1.5. At x equals 2, what is the rate of change? 3 over 2 still. And I don't know, for fun, how about 5? No, how about 4? Oh, well, we already said it's constant, right? It's unchanging. If you plot these points and connect the dots, it's a horizontal line. It's this horizontal line. This line is y equals 3 over 2. There's no x because it's constant. This function is our instantaneous rate of change function. It tells us what the rate of change, instantaneous rate of change is of our function at every x value. Which is kind of like, well, duh, it's constant. But are they all constant? Of course not. This one has average rates of change that are changing constantly. Wow, I didn't mean to use the word constantly like that. Always changing, there we go. But there is still a way to get a function that when x goes in, rate of change comes out instead of a y value. And that's what we're working on learning how to do. So this is not xy's. I'm going to scribble that little y out. It is not xy's. It's x and rate of change. All of its dependent values are rates of change of this function, rather than actual xy's of our function. Seems kind of dumb to do it with straight lines. So let us figure out how to extend it to not straight lines. Here we have the quadratic function x squared minus 6x plus 5. There's its graph. The directions say to use the table of values. By the way, these are all x, y's that are on this picture. Use the table of values to find the average rates of change on consecutive, that means back to back to back to back, equal length intervals of x's. And then we're going to put them in here. So this is from x equals 0 to x equals 1. The average rate of change is just the slope between these 2 points. So let's find the slope between these 2 points. y2 minus y1 gets me 0 minus 5 over x2 minus x1. So 0 minus 5 over 1 minus 0. Negative 5 over 1. Now we're not going to let the size of the interval change. We're just going to move to the next interval of x's. Now we're going to look from 1 to 2. Yes?
To get the negative 5, you plugged it in.
I did this. 0 minus 5 over 1 minus 0. I just did change in y over change in x.
Oh.
We're just finding the slope. So we don't have to actually plug anything in. That was done for us. They were just picked right off the graph. So for this 1 to 2, now we're finding the slope between those 2 points. Negative 3 minus 0 over 2 minus 1. That's negative 3 over 1. Now we find the slope between 2 and 3. 4 minus negative 3. That means negative 4, excuse me, minus negative 3. That means negative 4 plus 3. Negative 1 over 3 minus 2. Negative 1 over 1. Now go from 3 to 4. Negative 3 minus negative 4. That means negative 3 plus 4, 1. Over 4 minus 3, 1. 1 over 1. 0 minus negative 3. It's 3 over 5 minus 4. 1. 3 over 1. And lastly, the slope right there. 5 minus 0, 5. Over 6 minus 5, 1. 5 over 1.
How is 2 comma 3 and negative 1?
No. 2 comma 3 is the x value 2 to x value 3. So,
Oh, I was looking at the wrong one.
yeah. So you do negative 4 minus negative 3 or negative 4 plus 3. So negative 1 over 1. What we have down here, by the way, one more time, what we have here are 1, 2, 3, 4, 5, 6 average rates of change. And the span of the x's never changed. It was always a length of 1. And they were consecutive. See how both of these intervals include x equals 1. Both of these intervals include x equals 2. Both of these include x equals 3, so on and so forth. Okay? Now let's try to figure out what the change in the average rate of change was. We are literally talking about the change of rate of change, which is what we did yesterday. Remember we said if rate of change is increasing, then what do we know? If average rate of change or instantaneous rate of change, if rate of change increases, what does it tell us about our graph? Concave up. And if rate of change is decreasing, concave down. Look at these numbers. They're going up. That tells us our graph is concave up. Well, duh, we can see it. But it just really reinforces that idea. But by how much was it increasing? To go from negative 5 to negative 3, what do I have to increase by? Plus 2. Look at negative 3 to negative 1. Negative 1 to 1. 1 to 3. 3 to 5. It's plus 2 every single time. Isn't that neat? Yes, what's up?
Is every x squared graph like that?
He asked, is every x squared graph like that? Do you mean, where were you asking about, like what?
Like that same graph, like not like modifying or anything, just like indicating
So he wants to know if the change in average rate of change is always plus 2 for all quadratics. Yes, it is. So it's almost as if you have stumbled across a truth of calculus. What do you think the change in rate of change is going to be for cubics? How about that? 3. How about that? Anyway, it says use the results from the table of averages. No, using the result from the table of average rates of change above. Do you notice a pattern in the rates of change? Yes. What we know in the pattern of rates of change is that they are increasing every single time by 2. And so we could say formally in words, as x increases by 1, the rate of change increases by 2. The AROC increases by 2. Now it says, what can you say about the rate of change at the point x equals 3? Well, check this out. X equals 3 is right here at the vertex of this quadratic, right? X equals 3 is the place where this graph stops decreasing and starts increasing. Do you guys remember what it's called? I said it. When you're increasing, decreasing changes, what we call that kind of point? Ooh, that's when concavity changes as an inflection point. This is just increase, decrease changing. Not midpoint. It's a good try though. It's called in fact, all minimums and all maximums are called this. Turning point. I mentioned it, but we never formally wrote it down. So we're going to say because, so B/C, because f of x changes from decrease to increase at x equals 3, it is a turning point. So when you're decreasing, what is your average rate of change when you're decreasing? What kind of average rate of change do you have when you're decreasing? Negative. And what kind of average rates of change do you have when you're increasing? Positive. And if you're going to go from negative numbers to positive numbers, what must you always pass through? 0. That is why the instantaneous rate of change at x equals 3 is 0. Cool. So some essential facts that we have to understand. Over any length input value interval, meaning it didn't matter if we were going from 0 to 1 or from 0 to 3, as long as we didn't change that up. So if I wanted to go from 0 to 3, I'd go like from 0 to 3, 3 to 6, 6 to 9, 9 to 12. You see, like, we're allowed to do that. 1 to 3, 3 to 5, 5 to 7. It doesn't matter the length of the input value interval, as long as we don't change it up. The average rate of change for every linear function is always the same. Average rate of change for a linear function is exactly what Hunter said, constant. Now, if you took consecutive equal length input value intervals, like we have here, the consecutive meaning there were no gaps in them, the average rate of change of a quadratic function can be given by, well, we said that the change in the average rate of change of every quadratic was going to be 2. What you might not have caught on to, though, is that I could have used this and this to write myself a linear function. I could use this as the slope, and not so much these, but more like the values that would have fallen in between them to write a linear function. And that would have been the average rate of change of a quadratic function
So you're saying
in a y equals mx plus b format. No, you're good.
So you're saying the numbers in between, but I thought the numbers in between were what the plus 2 was.
Well, here, check this out. Notice that this interval is from 0 to 1, but this one was from 1 to 2. So looking at these two numbers and seeing that there's a 1 here and here, what do you, if you had to guess, what do you guess the instantaneous rate of change would have been at 1?
1.5.
Not, that's
Wow. The instantaneous rate of change.
-4,
Why?
because it's between -5 and -3.
But you said 1 and 1.
Yeah, because there's a 1 at the end of this interval and a 1 at the beginning of this interval.
Oh yeah, so I was thinking 0.5. But it's not 0.5, it's -4.
Yeah, so we predict a slope of -4 here, instantaneous rate of change, instantaneous rate of change at 2 of -2, instantaneous rate of change of 3 at 0. Oh, we already knew that. Instantaneous rate of change at...
Hello?
I'm literally going between the two numbers.
You said 3 and 3, 0.
Yeah, the instantaneous rate of change at 3 is 0, because that's halfway between -1 and 1. See,
Wouldn't it be 0 between 2 and 2 then?
no. Okay, you're thinking of the difference between the y, or the x values. I'm talking about the instantaneous rate of change at the x value.
At the x value.
What's the slope of this curve at this point?
0.
Yeah. At x equals 3, 0. Halfway between -3 and 1. Because the average rate of change here is -1. The average rate of change here is +1. The average of -1 and +1 is 0.
So for the 2 and 2 one.
2 and 2. None of these say 2 and 2. You mean at x equals 2,
At x equals 2.
which is right here.
Yes. How would you get -2?
Because that's the average of -3 and -1. Because x equals 2 exists in both of these intervals.
Oh.
Yes? Instantaneous rate of change is, for lack of a better way of saying it, the slope of the curve at one x value. Okay? You're technically not allowed to say slope at 1x because that implies you divided by 0. But for lack of better words, that's as good as I can make it. Okay? Anyway, the average rate of change over the closed interval a to b is the slope of the secant line. Okay, we already knew that. Okay. Here, I'm going to redraw something I've already done. I'm going to draw secant lines through these curves. This is concave up. Now we're going to say that the slope of the secant line is increasing. Slope of that secant line, positive. Slope of this secant line, positive but steeper. Slope of this secant line, positive but steeper still. Steeper meaning the slopes of those lines are getting bigger. So I can say if the average rate of change is increasing, a curve is concave up. But I can also say if the slopes of the secant lines are increasing, then it's concave up. Why can I say that? Because the slope of the secant line is the average rate of change. It's just another way of saying it. And the same thing happens over here with the negative secant slopes. There's a secant line with a negative slope. Here's the next, which would be consecutive, secant line with a negative slope. You can see it's steeper, so it's quote unquote more negative. That means it decreased. And then there's this one, which is steeper still, meaning more negative, decreased again. So again, I could say the average rates of change are decreasing, or I could say the slopes of the secant lines are decreasing. Those both mean concave down, because the slope of the secant line is the average rate of change. So now what we're going to do is what we did here, but instead of doing it for that straight line, we're going to do it for this quadratic. And we're going to try to develop an equation so that when an x goes in, an instantaneous rate of change pops out. So then I can tell you what the slope, quote unquote, remember you can't technically do it, but I can tell you then what the slope of this curve is at x equals 5. We predict and estimate that it'll be halfway between 3 and 5, because, which will be 4, because the number x equals 5 exists in two different places. So we're predicting that our function will give us a 5 goes in, 4 pops out as a slope. Let's find out. So using the function from example 2, which is this right here, right there, let's consider what the graph of the average rate of change for this quadratic function would look like. Our parabola is concave up because the average rate of change over equal length intervals is what? Positive means increasing. But why are we concave up? Because our rate of change is increasing. Because the rate of change is increasing, we're concave up. And what were we increasing by each time? 2. If we call that 2 the slope of our rate function, let's call it a rate function. If we say 2, which was how the rates of change were changing, if we say 2 is the slope of our rate function, or no, let's just say it is. We also noticed that our quadratic function went from decreasing to increasing at our vertex. And at the vertex, x was 3. And because it was a turning point, we know that the rate there is 0. Because the rate is 0, we would say that the slope is, well, not 0, we'd say the slope is, use a word, is constant. Meaning that slope is not changing there. We are going to use x, comma, rates of change to figure out this, yeah?
Isn't the slope at any given point constant?
No. We're not saying that the slope is constant. We're saying that, okay, how do I want to say this? The slope of this function, these slopes are all negative, these slopes are all positive. That makes this slope 0. Now, if we just had a graph, you could say you have zones of increasing, decreasing, and constant, right? We recognize zones of constant because they're literally horizontal. So we say that this place, it is considered a constant point because its slope is 0. Okay? We don't have a constant interval, we have a constant point. It's also known as a stationary point because it's not increasing, it's not decreasing. We call it stationary in calculus and in IB. So let's use our results from what we had before. We're trying to write this equation. We already know our slope. We said our slope is 2. We happen to have a coordinate that is x comma rate of change. We only have one. We have x comma rate of change here because we already know that the rate of change there is 0. So at our vertex, we have the point x comma rate of change at that x. Because we said at x equals 3, the rate of change is 0. Let's write an equation in y equals mx plus b format using that knowledge. Okay, well, we already know it goes y equals 2x plus b. This is going to act as an x comma y for us to help us solve for b. Here was the y value there. The x value there was 3. What that gave us is 0 is 6 plus b, which guarantees to us that b is -6. This is our, for lack of a better term, rate function, our slope function, y equals 2x minus 6. Yes?
Why is it 0 and not -4?
That's the y value.
Yeah.
But this isn't, this is x comma rate of change, not x comma y. Let's plot this. Crosses here and has a slope of 2. And then try to connect those dots with a straight line to the best of your ability. I would like for us to now use this thing to see what the instantaneous rate of change would have been at x equals 5. Let's look. I go to x equals 5, and I track it up to my rates of change, and I get an instantaneous rate of change of 4 at x equals 5. Now flip it over. Oh, look, the average between this 3 and this 5. So the instantaneous rate of change at 5 would have been the average between these two average rates of change. Isn't that neat? So for this quadratic, if you wanted to know what its slope was at x equals 10, it would be 14. Because you could plug 10 in here as an x value.
I was just plotting it. What are the little dotted lines?
That was me going to the point x equals 5 and tracking it up to see what its instantaneous rate of change was. This is our instantaneous rate of change, your IROC. I'll never write that again. I just didn't feel like writing all those words. So these are x comma rates of change of our parabola. What we want to do is we want to be able to generalize this. We want to show that this kind of thing works for all quadratics. In fact, we want to show that it works for all functions. So let's go to just some generic other function, x squared plus 2. Let's first find the average rate of change from 2 to 4. What we're going to do is we're going to say f of 4 is. Now plug 4 in, and you get 16 plus 2. Then we're going to find f of, which is just a y value, f of 2. Let's find our y value when x is 2. 2 squared plus 2, that's 4 plus 2, that's 6. Let's find our average rate of change, which again is just a slope. y2 minus y1 over x2 minus x1. Oh. The average rate of change between two known points happens to be a number. How about that? Okay? In fact, and this doesn't really mean much to you. It just happens to be the average rate of change between 2 points. It's the slope of the secant line that goes through those 2 points. But what if only one of the 2 points is known? What if I tell you it's x equals 2, or t equals 2, and the next one is just 2 plus h? Can we all agree that as long as h is positive, that 2 plus h is a bigger number than 2? Can we agree to that? This acts as our x2. Okay? This acts as our x2. So if we go to find our y2, we don't have a choice but just to write, well, replace x with 2 plus h. So replace x with 2 plus h. You do have to know how to FOIL. And then combine your like terms. I'm going to write it as, actually, yeah, 6 plus 4h plus h squared. There, I combine like terms. From up above, we already know what f of 2 is. Right where my thumb is, f of 2 is still 6. Let's find our average rate of change now between a known x value and a generic bigger x value. y2 minus y1 over x2 minus x1. On top, the 6's cancel. And on bottom, the 2's cancel. And this fraction reduces, because I can factor an h off the top, and I can cancel it off the top and bottom. My average rate of change ends up being 4 plus h. Huh.
Where did you get the y values?
I plugged the x in to there.
But when you plug the x in, I thought.
When you plug x in, you get a y out, right?
Yeah. Oh, okay. Yeah. Now I.
So this is y2, this is y1. This was.
You get the -2. How'd you get
I didn't get -2.
the -2?
It's x2 minus x1.
And x. Oh, okay. But sorry.
No, you're fine. And then, what if both things were generic, not just one of them? Let's find the slope between these two generic points. You're fine. y2 minus y1 over x2 minus x1. On top, there's no way to simplify because you don't have a function to plug into. But on bottom, the a's cancel. This is the average rate of change between any two generic points of a curve. This is known as the difference quotient, and it is the very first calculus thing that you have learned. Barely made it.